First, I wanted to clarify one point because naively, so what's the statement? So WIE obstructs, we proved one version of this, K linearly independent sections. That happens when I plus K is one more than the rank of E. So, but one thing to notice is that if I choose, say, K sections, and I look at the zero, and I order them, and I look at the zero locus, and I'm assuming transversality, at least to some extent, of one of the sections. Then, of course, if one of two vectors is zero, then a collection of two vectors is linearly dependent. So that sits inside the dependence locus of two sections. And we're looking there, and this would be the we're considering the Stiefel-Whitney class associated with the dependence locus of K sections. And really, what do I mean by dependence locus? All I would mean is looking at direct sum of sections and looking at the preimage of dep K. But remember that dep K is the image of dep K hat. So this could also, if I write it this way, I'm thinking about the image of this smooth thing is this dependence locus. And for example, if any of these inclusions is proper, then the obstruction of the larger one. So for example, if there's no further dependency of two sections than on coming from the zero locus of one section, then in fact, just for dimensional reasons, that obstruction would be zero, because any chain would of the appropriate codimension, codimension, I guess you would say, the appropriate dimension, wouldn't evaluate except to zero on that dependence locus of two sections. So really these are, normally you might think of an obstruction theory like, well, do you have one non-zero vanishing section? If so, then it makes sense to ask, well, can I have two, etc. And here what we're doing is we're measuring each of these cohomologically or homologically. So the normal way you might think of a sequence of obstructions isn't actually applicable here. We're just really these are loci. Let's again ignore the smoothness, and you're asking whether they bound. And just because we have these inclusions doesn't mean that we require the vanishing of one in order to consider the next. Okay, so I wanted to move on to some applications and calculations in particular using the axioms. This is contained in this wonderful section 4 of Milner and Stasheff. But let me first say that, for those keeping track at home, this obstruction theory is in chapter 12 of Milner and Stasheff. And actually, a lot of what we did with tome classes is really equivalent to section 11. So that's the reordering. You compare, and we can make this a little exercise if you want, compare with our definition with theorem 12.1 of Milner and Stasheff. So that's just a guide, but let's talk about some calculations. So, well, one of the first things you'd want to know is whether something is always 0 or not. So could it be that even though we define these, they're basically almost always, or well, we showed that, or we have shown from this definition, and it's taken as an axiom, as one of the axioms, that W1 of the Mobius bundle is non-zero, but maybe that's the only one. Could, for example, some Stiefel-Whitney class be identically 0? Well, let's consider first. Let's note that that continues if I take the tautological bundle over the Grassmannian of lines in Rn or Rn plus 1, say. This is also not 0, and that's because this tautological bundle, which is the Mobius bundle over RP1, is the pullback of the tautological bundle in Rn plus 1, the map given by inclusion of R2 and Rn plus 1. Therefore, lines in R2 includes in lines in Rn plus 1. Easy to check you've got that pullback. This iota map is isomorphism on H upper 1. So so we must have that the first Stiefel-Whitney class of this tautological bundle. At some point, by the way, I'll maybe just start saying gamma 1 instead of gamma 1 over which particular projective space using context. So anyways, pullback on cohomology is an isomorphism on H1. So because this pulls back to something non-zero, it must be non-zero itself. So let's, for example, now calculate using the workhorse Whitney sum theorem. So let's calculate the Stiefel-Whitney classes of, say, gamma 1, R3, gamma 1, R3. Again, maybe we should just say gamma 1 plus gamma 1. Both of these are RP2. I'm taking the internal direct sum. Whitney sum, of course, holds for external as well by naturality. You could, in fact, take that as the axiom. They're equivalent by naturality. So what you have is that W1, I'll omit the bundle altogether, is W0 of the first factor times W1 of the second, plus W1 times W0. And so what do we get? Well, this is 1 by the axiom. W1 is X, so X is the non-zero element in H1 of, say, RP and in general by abuse. But then I have this term. So we get that there has no W1, but now let's consider W2. Again, the Whitney sum formula says now I'm going to get what? I'm going to get first 1 times 0. It's a line bundle, so it has no W2. But these W1s are both X, because it's 2 copies of the same bundle, and it's W1 we just argued was that non-zero class in H upper 1. And then the third term is that, so this is just X squared. And so so that's not 0. So that's an example of a non-zero W2. And you know, we can continue to show that Wn of a direct sum, so similarly, Wn of a direct sum of n copies of gamma 1 Rj for j bigger than or equal to n plus 1 is not 0. So we're not getting the theory of the empty set or something like that. We've got some interesting cohomology classes. We can do substantially better than that. But first, let's reformulate our workhorse Whitney sum formula. Let's define W of E to be this silly sum. It's just going to be the sum over all Stiefel-Whitney classes. And I say silly because we normally don't think of adding cohomology classes in different degrees. So this is just formal. It's in the direct sum of the cohomology. So if I've got rank n, then these are the possible non-zero ones in the direct sum of the cohomology of whatever the base is. I guess we're generally calling it a manifold. So this seems formal. It actually, especially when you study things like K-theory and the Chern character, you realize that, wait, maybe these are start to be some things, phenomena across dimensions can be tied together. And so it's actually, there can be more meaning. But for now, this then leads to a reformulation of the Whitney sum formula. Says that W of E plus F is just W of E times W of F. So that sort of takes these kinds of calculations that we just made for this direct sum of line bundles over RPN and lets us just sort of, it's a convenient shorthand. It'll save us a little work. For example, I'm going to consider now the external direct sum of these line bundles. And I'm just going to think about in something large enough. Suppose I have m of these. So that's my E. It's going to sit over each of these as an RPM. But again, I have m of those. So standard calculation in first-year algebraic topology using the Kunith. Remember, we're doing Stiefel-Whitney classes, so I didn't say at the beginning, but as long as we're doing Stiefel-Whitney classes, all cohomology is mod 2, unless stated otherwise. The cohomology of this space is the tensor product of the cohomologies, and I can really just think of that as I guess it's modulo some powers, but we can always choose n big enough. The shorthand for this is usually to just talk about RP infinity. I'm going to stick with finite dimensional just to remind ourselves that, oh, wait, our Stiefel-Whitney classes are only defined over manifolds. We need to work with limits and inverse limits to sort of use that definition more broadly, but we can stick with manifolds here. But the relations that we get by doing a finite dimensional RPN, if we choose n large enough, those never come into play. In any case, now let's look at the total Stiefel-Whitney class of E. Well, it's just the total Stiefel-Whitney class of one of the direct sum factors. And so that's, each factor is, say, 1 plus x1 for the first factor times 1 plus x2. So it's just a product of 1 plus xi. The higher Stiefel-Whitney classes of each of those line bundles is 0. The ith Stiefel-Whitney, the first Stiefel-Whitney class on the ith factor is just the x sub I, that generator. We're really not gonna, we're gonna do one other piece of geometry, but we're really milking this tautological line bundle over RPN for all it's worth. In any case, you may or may not, I hope you are familiar with the fact that this is some product which goes by the name, its degree 1 is called sigma 1 in the xi. Its degree 2 is sigma 2 in the xi, etc. And what our algebraist friends tell us is that these are these generate a polynomial subring. So the sigma I generate a polynomial subring of this polynomial ring. Again, maybe I'm taking a limit for it to really be polynomial. Well, actually, yeah, it's fine because we're again, I'm only up to the sigma m symmetric polynomial. So what does that mean? Well, this is going to be W1 of E, W2 of E, etc. So there's no relation among any of the powers of these W's. Again, letting in be sufficiently large. There's no relation. So that implies there can be no universal relations. Among these WIs. So we started with just being happy that we could prove that some of them are non-zero. That's showing there's no universal relation of the form, say, W3 equals 0, because we could find something where it's not 0. This says any polynomial in the WIs, any polynomial you name, this particular bundle will have that that product of Stiefel-Whitney classes non-zero, and so that polynomial in the Stiefel-Whitney classes couldn't be 0 universally. Okay, so that's so that means that we've defined these, we've set out their properties. We still need to establish the Whitney sum formula. But one thing you often do when you define something is, well, how many do we have of them? And we now know that sort of we have all that you would expect you possibly could get. You've got any polynomial in the Stiefel-Whitney classes is going to be what we call a characteristic class. Okay. Next, we're going to do one more bit of geometry. So it's sometimes interesting to keep track of, where is geometry happening. So for example, Poincare duality you can use to get the cup product structure on projective spaces, and there's so much topology that comes from that, but it really is the geometry of Poincare duality. Or if you're a fan of Thom cochains, it's this basic intersections of linear subspaces in projective space sort of works as projective space is defined to make it work. So we're going to do one little bit of geometry and get some remarkable consequences, remarkably strong consequences. So here's a proposition or a theorem that the tangent bundle to RPN is isomorphic to, we talked about linear algebra of bundles. I'm going to take HOM of, maybe I'll start dropping gamma 1 into gamma 1 per. Again, gamma 1 is in R n plus 1 if we want. Okay, so so why is that? Well, let's draw a picture. We've got an element L in RPN. Let's think about where it hits the unit sphere. Say it's at some x and minus x. And then the naive guess would be that, well, if we thought about the tangent space of the sphere, it was the perp. So you would guess that just as for the sphere, that the tangent space at L of RPN should be identified with L perp. But if you look at the statement of the theorem, that would say the tangent bundle was gamma 1 perp, not this HOM. And what happens is, well, if you think about it for a second, we've got x and minus x are identified on the sphere. We're trying to use the geometry in Rn, not really Rn plus 1, not Rpn, but Rn plus 1. So I have to keep track of those identifications. And the point is that that these that those points would give me the same let's see. So let's see. Let me put a minus there. Sorry, I meant to do that. That I would have a different orientation on that space, so to speak, if I thought about it from the other direction. So so indeed, the identifications really that we want are, if I want to think about, so I want to think about tau RPN as pairs xv or minus x minus v, where say x is on the unit sphere and x is perpendicular to v. So if I think about those identifications, then in terms of a pair, I get that TLRPN can be identified with, so this was wrong, can be identified with HOM from L to L perp by sending xv, which again is the same as minus x minus v, to the homomorphism, which sends x to v. Okay, so yeah. So it's pretty similar to the calculation we made for the sphere, but there's this twist, literally almost. And then there's some cleverness. Some remarkable cleverness. I won't call this a theorem or a proposition, I'll just call it cleverness. Oops. It's okay. And the cleverness is that actually we can start with this, and if I just add a trivial bundle, and notice that this is now rank n plus 1, I get n plus 1 copies of the tautological bundle. Which is kind of odd if you think about it. This first thing obviously has a section, because I put that epsilon 1 there. thing on the right looks like the direct sum of a bunch of things which don't have sections. But again, we're over RPN. And so n plus one of these is sort of greater than the dimension that you would expect things to be independent. So, well, why is this? Well, first note that Hom gamma 1 to itself is a trivial bundle because it's a line bundle with a section. I forget whether we talked about that or gave it as an exercise, but if neither happened, a line bundle with a section is trivial. I think we did. In fact, in sections, I'm pretty sure we did that theorem. So that means that this tangent bundle of RPN plus epsilon 1 is the same as, well, we just said that the first thing is Hom from gamma 1 into gamma 1 perp. The second thing we just identified with Hom from gamma 1 to gamma 1. Linear algebra says this is same as Hom from gamma 1 to epsilon n, n plus 1, because direct sum of Homs is Hom into the direct sum, and the direct sum of gamma 1 perp and gamma 1 is epsilon n plus 1. And, but then that's a direct sum of n plus 1 copies of gamma 1, because a metric on a bundle gives an isomorphism of the bundle with its linear dual. That's essentially what a inner product is. It's an isomorphism, choice of isomorphism of V and V star. That's true for bundles as well. And well, this is over RPN, and so so we have this the existence of a metric. Great. So here's a corollary. Yeah, so corollary. The total Stiefel-Whitney class of the tangent bundle to RPN is that 1 plus x in degree 1 to the n plus 1. So that implies that Wi is equal to n plus 1, choose I, times x to the I, just by the binomial theorem. So, so again, we get lots of examples of non-zero Stiefel-Whitney classes. One thing that is then a corollary of a corollary, this implies that RPN cannot be a Lie group isn't the manifold that underlies a Lie group if n is not some power of 2 minus 1. Because binomial coefficients mod 2, some binomial coefficient is not vanishing unless I've got to a power of 2. By the way, the very top one, Wn plus 1, is 0 always, just because we're over RPN, and so x to the n plus 1 is 0. And what that then means is that if we're tossing out those top binomial coefficients, or we're taking off the right-hand side of Pascal's triangle. So what happens then if you do have a power of 2, or in other words, the RP n is 1 less than a power of 2, that row of Pascal's triangle vanishes. Why is this? Well, I mean, I guess I didn't say it, but as a great example, this is because a Lie group is what's called parallelizable. That means its TG is the bundle G cross Rn, where n is the dimension. So yeah, so that's fun. That says don't look for all sorts of Lie groups, and you can imagine in general. So these Stiefel-Whitney classes obstruct of the tangent bundle obstruct manifold being a Lie group. Place pretty substantial restrictions on what can be a Lie group. Here's another consequence, and then I'm going to call it a day, and then we'll talk about, I'm not covering all of chapter 4 because it's so nicely done, you might as well read it, but we'll talk about what we're doing from here. So here's the theorem. I'll make it concrete. This is in Milner and Stasheff, this example. RP9 cannot immerse in R14. So immersion just means that the derivative is non-zero, full rank everywhere. That implies that it can't embed in R14 in particular. So why is that? Well, if in general, if M immerses in some R, P or Q or something like that, then you have the, well, because the tangent bundle of M plus, if you have an immersion, you have a normal bundle. You don't need to be an embedding to have a normal bundle. And what we can do is say, then you, so this implies that the tangent, the Stiefel-Whitney classes of the tangent bundle imply those of the normal bundle. And what we're going to find, so if Wi nu isn't 0 for some I, that means that that P must be greater than or equal to the dimension of M, which is, say, M plus I. So that's the strategy. So in this case, we find that this total Stiefel-Whitney class of the tangent bundle of RP9 is, well, it's 1 plus x to the 10th power, which is 1 plus x squared plus x to the 8th. Remember that the top power doesn't occur because we're on RP9, so x to the 10th is 0. So that means that the total Stiefel-Whitney class of the normal bundle of RP9 is something that, when multiplied by that, is the total Stiefel-Whitney class of the trivial bundle. So in other words, it's 1 plus x squared plus x to the 8th. And you can use power series thinking, if you're used to power series, which I'm assuming everybody is. But the point is that things are only going to be non-zero at a finite stage. And also, we are working mod 2, but the algebra of this power series division works the same. And so if I just, 1 over 1 plus x is 1 plus y is 1 plus y squared. If you work that out, in this case, it's 1 plus x squared plus x to the 4th plus x to the 6th. No x to the 8th, because y is going to have an x to the 4th, which is x to the 8th. It's also going to have an x to the 8th to the 1st. Those cancel. And then there can be nothing else. But this is the culprit now. So this implies that the rank of the normal bundle is at least 6. So it can't equal 5. So again, RP9 can't immerse into R14. And that's a theorem in topology for sure. So this just sort of blows away. It would be remarkably hard to try to come at such questions without the theory of characteristic classes. You establish them and their properties, and yeah, you get this pretty cheaply in the end. Again, with the Whitney sum formula being something that we're going to have to work to establish, but now we appreciate some of the payoff. So this is taken from the fourth section of Milner and Stasheff, which I think is some of the loveliest writing, some of the greatest payoff for some theory that I know of. There's other applications there as well, although I think I've covered a good number of them. I recommend reading that chapter, cover to cover, every single page. I recommend doing all the exercises. I haven't recommended any exercises, but let's just say that for those studying this, do the exercises in that section of Milner and Stasheff. And by the way, I'm going to pause. I've been giving lectures 3 times a week, in part to give people time to work with that chapter, and in part to give people time to kind of catch their breath and catch up. I won't be broadcasting a lecture this Saturday, so it'll be a good, I guess, 5 days until I broadcast again. I hope this finds everybody well, and yeah, I'll sign off as soon as